So, now we will start module 4, and in this module we will complete the discussion on matrices. We will talk about matrix rank, inverse of matrix, eigenvalues, eigenvectors, and then we will talk about special matrices and normal modes. So, today I will be talking about the rank of a matrix and the inverse of a matrix. Okay. So let us get to the rank of a matrix. Now, in order to define the rank of a matrix, it helps to treat the matrix as a collection of vectors. So, your matrix is treated as a collection of vectors. Okay. So, how do you think about this? And you can treat it either row wise or column wise. So, suppose you have a matrix, okay, a typical matrix. So I will just take a our typical matrix A11, A12, etc. up to A1n, A21, A22, all the way up to A2n, and then similarly all the way. Let me take AM1, AM2, all the way up to AMN. So, this is an m by n matrix. So, this is an m by n matrix. Now, I said that you can treat this as a collection of vectors. So, you can think of each row as a vector. I will just use a different color. So, you can treat each column as a vector in this way. So, you can think of this as a collection of vectors either as column wise, or row wise. So, how do you think of it? So, suppose I want to think of this as a collection of column wise vectors. So, column wise I would just say A11, A21, I would treat this as one vector. Then I would think of another vector A12 up to AM2. So, you can see all the way. So, what I am doing is I am treating this column as a vector, this column as a vector, each of these columns as a vector. Okay. So, all the way up to A1n, A2n, all the way up to AMN. So, if I treat it column wise, I have n vectors, n column vectors. Okay. Now, alternatively, and you can see this, I don't really need to emphasize this. This is row wise. So, if you think of it row wise, you can think of it as m row vectors. Okay. And these row vectors will look like A11, A12, A1n. Then you will have, similarly you can have A21, A22, all the way up to A2n, and then you can have various vectors all the way up to AM1, AM2, all the way up to AMN. So sometimes it is very useful to think of this matrix as a collection of vectors, and you can think of it either as a collection of m row vectors, or you can think of it as a collection of n column vectors. Okay. So, this basic idea of thinking about matrices as collection of vectors is what you need in order to define a rank. Okay. Once you think about this matrix as a collection of vectors, then the question you can ask is, are these vectors linearly independent or dependent? Okay. So now the rank is nothing but number of linearly independent rows or column vectors. So if you want to find the rank of a matrix, what you do is you think of this matrix either as a collection of n column vectors, or you can think of it as a collection of m row vectors. Okay. Then of these, so suppose you are thinking about it as n column vectors, then you can ask the question, how many of these column vectors are linearly independent. Okay. So you will have some number which is less than n, okay, as a rank of a matrix. Alternatively, you could think of row vectors, okay, and you will get a number. Now you ask how many of these row vectors are linearly independent, you will get a number that is less than m, okay, and that is the rank of the matrix. Now what is important is that it does not matter whether you take row or column vectors, you will get the same rank, and this is fairly easy to show. So it's I will just underline this in a different color. So does not matter if rows or columns are used. Okay, so the idea is that you can use either row or column, and you are fine to calculate the rank. Okay, so what this implies is that this implies that your rank must be strictly less than or equal to the minimum of m and n. Okay. So what that means is if you have fewer rows than columns, then the rank must be either equal to or smaller than that number of rows. Similarly, if you have fewer columns than rows, then the rank must be lower than the number of columns. Okay. So rank has to be less than number of rows, and it has to be less than or equal to number of rows, and less than or equal to number of columns. Okay. And so we can write this as saying that the rank is less than the minimum of the number of rows and the number of columns. Okay. And remember, you have an m by n matrix. This is for an n by m matrix. Okay. So now this is what it tells you the rank, and you can immediately see that since we already said that the maximum number of linearly independent vectors is equal to the basis. Okay. So maximum number of linearly independent vectors in any space is basically the number of vectors in the basis. Your rank will give you some, if you look at a vector space and you consider various vectors in that space, okay, then the maximum number of linearly independent vectors is related to the basis. So in that way you can also relate rank of matrix. Rank of matrix has to be less than or equal to basis. So it is less than or equal to number of basis vectors. Okay. So it is less than or equal to number of basis vectors in the appropriate space that you are considering. Okay. Now let's go and see some examples, okay, where you can determine the rank of a matrix. So suppose I take a matrix that looks like. I'll just take some examples. So 0, 1, 2, 2, 1, 3, okay, and I take this as 2, 2, 5, okay. Now if you want to determine the rank of a matrix, you can use either the rows or the columns. So rank using rows. So if you use rows, okay, then you have 3 vectors. So you have this vector 0, 1, 2, you have another vector 2, 1, 3, and you have vector 2, 2, 5. Okay. And if you want to ask how many of these vectors are linearly independent, okay, you can immediately, just by inspection, you can see that rank equal to 2, because 2, 2, 5 is equal to 2, 1, 3 plus 0, 1, 2. So in this case you can immediately see the rank, you can see that the rank should be equal to 2, because I can write this third vector as a linear combination of first 2 vectors. Okay. And not only can I do that, okay, but addition to that, you can see that if you take the first and second vectors, they are clearly linearly independent. So the rank is not 1, rank is equal to 2. So in general, you can take any matrix, you can do the same using columns and you will get the same answer, okay, and basically the rank is independent whether you take rows or columns. All right, now we can ask the next questions as to where do you use the rank. Okay. So now rank of a matrix is actually extremely useful in solving linear equations. Now you remember that we wrote your system of linear equations. Okay. So your system of linear equations, we can write it in matrix form. So if you remember, we had it A11 x1 plus A12 x2 plus all the way up to, let us say, A1n xn is equal to B1, and you had this system of equations. So you had A21 x1 plus A22 x2 and all the way up to A2n xn equal to B2, and we had the same thing all the way up to AM1 x1 plus AM2 x2 plus all the way up to AMN xn. This was equal to Bm. Okay, and we wrote this whole system in a compact matrix form A, which A is a matrix, x is a vector, and this is equal to B. So we had this simple notation where A was basically this matrix that we had before with coefficients A11, A12 and so on. Now if you remember, we had when we were solving linear equations, we said that in order to be able to solve, okay, in order to be able to solve these equations, okay, the equations should be both sufficient and consistent. So should be sufficient and consistent. Okay. So in general, we said that the number of unknowns should be equal to the number of equations. Okay. So in general, we said that not only the number of unknowns should be equal to number of equations, but also that the equations should be internally consistent with each other. Okay. You cannot have equations that are inconsistent. Okay. So so now we can express this in a very nice form using the rank of a matrix. Okay. So this condition can be expressed in a compact way using rank of a matrix. So we will define augmented matrix A tilde. Okay. So we define an augmented matrix A tilde. Okay, which what does it look like? It basically looks like a matrix that is formed. All these are just A is here, and then you put the column of B right on the right side. So you have all the elements of A, okay, and then you have one extra column containing elements of B. So this is a M cross n plus 1 matrix. Okay. So now if you define this M cross n by 1 matrix A tilde, okay, which is called the augmented matrix. Okay. Now what is the condition for the system of equations to be both sufficient and consistent is that rank of A should be equal to rank of A tilde. So the rank of A should be equal to the rank of A tilde, and this should be equal to number of unknowns. Okay. So if this condition is satisfied, okay, then you know that the equations have a unique solutions. So then equations have unique solution. unique solution. Okay. So, if the rank of A equal to rank of A tilde, okay, then you are guaranteed that the equations are consistent. Now, further if the rank is equal to the number of unknowns, then you know that the equations have a unique solution. Okay, number of unknowns. So in other words, you can say rank is equal to minimum of m by n. So it is whichever is less between m and n, so it should be equal to that. Okay. So then you can be sure that the equations have a unique solution. Okay. Now this is a very powerful result, because you can determine the rank of A and rank of A tilde fairly easily just by checking for linear independence, and you can use this to actually say whether your equations are consistent or not, whether they have one solution. You can also extend it to other cases. You can ask questions like what happens if rank of A is let us say less than or equal to minimum of m cross n, okay, but rank of A equal to rank of A tilde. Okay, so suppose you had a case where the rank of A is equal to the rank of A tilde. Okay, so this guarantees consistency, ensures consistency. That means the equations will not be inconsistent. Okay, and when rank is less than or equal to the minimum of m and n, okay, you can have more than one solution. Okay, so that means you have some equations that are actually dependent on the others, and what that means is that you can have multiple solutions. So rank of A less than number of unknowns. So what I meant to say here is that it should be strictly, so if it is less than the number of unknowns, okay, so if your rank is less than the number of unknowns, okay, then you have multiple solutions possible. Okay, and we'll see examples of this over the course over the next few lectures. Okay, but basically this way of using ranks, okay, you don't need to actually check each of the equations to see whether they are consistent or not. You can directly use the idea of ranks to check for consistency. Okay, so now what happens if we have too many equations, and too few unknowns? Okay, we have too many equations and too few unknowns. Okay, then you would say that some of the equations are redundant. If they are consistent, okay, then they have to be redundant. So if rank of A equal to rank of A tilde, okay, then equations are consistent, and solution exists. Okay, so if you have too many equations and too few unknowns, okay, you can but if the equations are consistent, then the solution will exist. Okay, so even if you have too many equations, okay, so long as you have rank of A equal to rank of A tilde, you are guaranteed a solution. Okay, now if you want a unique solution, okay, then the number of unknowns should not be less than the number of equations. Okay, so then you can ensure that the solutions are consistent. Okay, so if you have too many unknowns and too few equations, okay, then multiple solutions. So I'll just write this explicitly. So if rank A equal to rank A tilde, then the equations are consistent and solution exists. Okay. Now if we have if m is less than n, so if m less than n, okay, then multiple solutions or more than one solution. Okay, then more than one solution exists. Okay, so if m is greater than equal to n, okay, then unique solutions. Unique solution. Okay, so this is the basic use of rank in solving linear equations. Okay, now next thing I want to talk about is the inverse of a matrix and how we use the inverse of a matrix in solving linear equations. So we had already seen earlier that if you have a matrix A, then A inverse, so this is called the inverse of A. Okay, this is called the inverse of A. Okay, this is equal to A inverse A equal to I. So again we will restrict to square matrices. Okay, so now when you have a square matrix, you know that the matrix can have an inverse, and if the inverse exists, it is unique. Okay, and the inverse satisfies this equation. So now suppose I had an equation Ax equal to B. So suppose I had my matrix, my system of linear equations that we had earlier. Okay, then you can immediately see that this implies X is equal to A inverse B. A inverse is a matrix. So suppose I multiply both sides by A inverse. Okay, then you can clearly see that A inverse A is nothing but the identity matrix. Okay, so this is what we call the identity matrix. Okay, and what you have is that I can write X as A inverse B. Okay, so basically if I know the inverse of this matrix A, then I know the solution. Then I can immediately solve for B. So suppose I have a set of equations and I write it in matrix form and I calculate the inverse of that matrix, I immediately know the solutions of those set of equations. Okay, now you have already seen solving a system of equations using Cramer's rule. Okay, so now we can see what is the connection. So when you solved equations using Cramer's rule, then we saw determinants coming in. Okay, so now here this gives another solution using inverses. Okay, so compare solutions using determinants, that is what we called as Cramer's rule, and using inverse. Okay, so what I mean is that you have the same vector that can be expressed as two different ways. One is using this inverse of a matrix and the other is using determinants. So what that implies is that there should be a relation between inverse and determinant. Okay, so just based on this you would conclude that there should be a relation between the inverse of a matrix and the determinant of a matrix, and various determinants involving matrices. Okay, so let us write an expression for inverse using determinants. I will just write the expression, it is fairly easy to verify. Okay, so suppose I have a matrix A. Okay, I can write A inverse in the following form. I can write it as 1 divided by determinant of A, and I'll just say determinant of A. This is the determinant of the matrix. Okay, and A inverse is a matrix. Okay, so it should have various terms here. What are the various elements of this matrix? So, the first element I will call it as A11, I am using the notation of capital A11. Okay. This is A, not instead of 1 2 I will write A21 here, and I will write A12 here all the way up to A1n, and here I go all the way up to AN1, A22 and all the way up to ANN. Okay, so what is A11 is called the cofactor of A11. So, we saw earlier that the cofactor of any element, okay, is the value of the determinant you get when you remove that row and that column, okay, is the value of the determinant of the matrix obtained by removing that row and that column. Okay. So, each of these is a determinant. So, A11 is an n minus 1 cross n minus 1 determinant. So, this is a n minus 1, it's the determinant. What I mean is it's the determinant of a matrix of size n minus 1 times n minus 1. Okay, and once again let me remind you what the cofactor is. Okay, so the cofactor, if you had a matrix A11, A12, A1n, A21, A22, A2n, AN1, AN2 up to ANN. Okay, so if you had a matrix like this, let us say if I want to calculate cofactor of I will just take some element. Okay, let me take A13 or let me take A23 that will make it more interesting. So, suppose I have A23 here. Now, if I want to calculate the cofactor of A23, okay, then this is the second row and the third column. So, what I do is I want to calculate the cofactor of this element, okay, and what I should do is I imagine that I consider a matrix where this row and this column are removed. Okay. So, if I remove this row and this column, and then what does my matrix looks like? Now I have to start from the A23. Okay. So, the matrix now will look the following way. So my cofactor is the determinant of this matrix, and that matrix is given by the following way. So if I remove this row and this column, okay, then what I have is a matrix that is starting with this will be A34. Okay, so this matrix starts with A34, A35 all the way up to A3n. Okay, so then you go all the way up to A3n. Okay, then you are still left with A31 and A32. So it comes all the way up to A31, A32. So that's how you write the cofactor. Then in the next row you will have, next row will start with A44, A45, and you go all the way up to A4n, A41, A42. So you go all the way up to AN4, AN5, ANN, AN1, AN2. Okay, so that is what you will end up here with this last row. Okay, then you have to come back to the first row. So then you still have one more row, which is A14, A15 all the way up to A1n, and then A11, A12. Okay. So this is an n minus 1 by n minus 1 matrix where you have removed the second row and the third column, okay, and you take the determinant of this is what is the cofactor. Okay. So the cofactor of any element of a matrix, okay, is obtained in this way, and the inverse of the matrix can be expressed in terms of cofactors. Now notice that there is a determinant that appears in the expression of the inverse. Okay. Now, and it is a 1 over the determinant. Okay. So, what this implies is that if of A equal to 0, then that implies matrix inverse does not exist, A inverse does not exist. Again a very powerful result. Okay. If the determinant is 0, okay, then the inverse does not exist. Okay. And this is actually a very useful property of matrices, that you can immediately tell whether you can invert a matrix or not by looking at the determinants.